Hello friends, in this video today we are going to discuss about special theory of relativity. So first let me tell you what is frame of reference. So frame of reference is a space where we make observations and measurement of physical quantities. Suppose this is the earth surface and a person is standing here on the earth surface. Suppose this is the observer O and a bird is flying. Okay, a bird is flying. He is observing. The observer is observing a bird is flying. Okay, so so as the person, as this observer is on earth surface, so earth, for him the earth is the frame of reference for this person. Okay, and a frame of reference may be at rest or maybe moving at uniform velocity with uniform speed. Okay, suppose now you are standing here on the this is the earth surface and a car is moving on the earth surface and a car is moving. Okay, so here you see the observer sitting inside the car. This is suppose O this and this is O this observer, and so here the person is standing on the earth surface. For him frame of reference is earth, and the person who is traveling sitting inside the car, so his frame of reference is the car. And if he observes, suppose the observer O this observes O and the observer O observes O this. Now you see there both are in motion relative to each other. Okay, so what we can say that what is a frame of reference. So we can define frame of reference as this: a frame of reference is a space in which we are making observations and measuring physical quantities. So that is what frame of reference. So there are two types of frame of reference. One is inertial frame of reference, inertial frame of reference, and another is non-inertial frame of reference. So what is the difference between these two, inertial frame and non-inertial frame? So inertial frame means the frame which is at rest or it may be moving with a constant velocity, and non-inertial frame is a frame of reference that is accelerating. Okay, that is not only moving with constant velocity, it is accelerating. Okay, it must be accelerating or rotating. If it is rotating or accelerating, then that inertial frame is called, sorry, that frame of reference is called non-inertial frame. So hope you have understood this. So now let us take two situations. Let us assume two situations. Now you see, suppose we have three fans here. One is A, is B, and C. A and B both are standing near a road. This is the road, suppose. And one friend is traveling in a car C. This is C. And here you see A and B, with respect to each other, they are at rest. But with respect to C, they are moving. Okay, if the car is moving with a speed of suppose 50 km/h, then with respect to C, these two friends A and B are also moving in the other direction, in opposite direction, with the same speed 50 km/h. per hour. And for these two friends A and B also, the friend that friend C inside the car is moving in this direction with 50 km per hour. So they are these two A and B are at rest relative to each other with respect to each other. So they are relatively at rest, and C is moving with respect to A and B. So we can say there is nothing like absolute rest or in absolute motion. So let me explain one more example. Suppose instead of C only, suppose if we consider two friends C and D, suppose uh, another person is there, suppose D, and both are moving in the car, both are in the car, they're traveling with the speed of 50 kilometer per hour, but this C and D, with respect to each other, they are at rest. Okay, so when we are standing on the earth surface, then we say, generally we used to say we are at rest, but actually we are not at rest. We cannot say that we are at absolute rest, or when we are traveling we cannot say that we are at in absolute motion. Suppose here you see, now let us assume two friends are in the space where, and around them there is nothing to assume as a frame of reference. These two friends are in space, okay, not on earth, they are in space, and around them there is nothing to consider as frame of reference. Then they are at motion or they are at rest. They will determine that with respect to each other. Okay, so they will observe that with respect to each other they are at moving, or they are they are at rest or they are moving. Okay, if there is no there is nothing around them to consider as frame of reference. So hope you have understood that. Now you say, let us consider another case. Suppose there are two cars moving on the road with different speeds. This is one car, suppose, and another car is this, and its speed is suppose 40 kilometer per hour, and it is moving with 50 kilometer per hour. So now then, with respect to this car, the speed of this car will be 10 kilometer per hour. Okay, so that means speed of this car relative to this is 10 kilometer per hour. And at the same time, for a person, suppose he is standing near the road on which these two cars are moving, for a person which is near the road, standing, which is at rest on the earth surface, then for him the speed of this car is 50 kilometer per hour and the speed of that car is 40 kilometer per hour. Okay, but speed of this car with respect to this is only 10 kilometer per hour. That is what relative motion. So now let us assume the same situation in space. Suppose a beam of light is traveling in space in vacuum. Okay, and you are sitting inside a spaceship, suppose. Okay, so here is an observer sitting inside the spaceship. Then the light is moving with the speed c. The spaceship is moving with the speed, suppose v kilometer per hour. Then with respect to this person inside this spaceship, the speed of light should be c minus v kilometer per hour. But in vacuum, the speed of light is always constant. That means, so though this person inside inside this spaceship is moving with velocity v and light is traveling with the speed of c, but this observer inside this spaceship will observe that the light is moving with velocity c. Okay, so now let us take another situation. Before that, let me tell you the postulates of relativity. What are the postulates of a special theory of relativity? There are two postulates. First one is all the laws of physics. All the laws of physics holds hold in all inertial frame of reference. So that means all the laws of physics, including Newton's law, Maxwell's theory of electromagnetism, these all laws that we have got in physics are those are applicable in all inertial frame of reference. And next postulate is that here you see light travels in vacuum. Okay, in vacuum, that travels in vacuum at constant speed. At constant speeds. That means I have already given you the example that suppose that a light beam of light is traveling with the speed of c, and a person or an observer in a spaceship, so he is observing the light and he is traveling with the speed of v, then generally this observer should observe the velocity of light c minus v, as they are moving in the same direction, and obviously c is greater than v. In that case, for this person inside the spaceship, the speed of light should be c minus v, but he will observe it c, because the postulates of a special theory of relativity says that light travels in vacuum at constant speed. Okay, it doesn't matter you are traveling or you are at rest in vacuum, but light is always constant. Speed of light is always constant in vacuum. Okay, remember that. Now let us take another example. So here is the earth surface, and there is an observer on the earth surface, and so and there is a clock with him, and there is a suppose instrument such an instrument that emits light, and there is a reflector also in opposite to the direction of light in which it is traveling to reflect the light. And after incident, it will reflect this light. Okay, so now you see, so this is the light emitted by this source, and there is also a receiver or detector that will detect a reflected light, okay, from the reflector. And suppose this distance is d, small d. Okay, so this light when it will reflected back, it will travel the distance twice. That means distance traveled by this light is twice the for an observer in the space. Okay, so now let us assume the situation like this. So this observer O this, and this is observer O on the earth surface, and here is also a clock to measure time. Now you see, so this system is moving with the instrument and the observer, and with the instrument it is moving. Now you see, this instrument that emits light and reflect lights, this instrument and this observer moving with the same speed in this direction, and in that case, according to relativity, so this observer O this will observe that this light, when it is emitted from the source and reflected back to the detector again, this, if this distance is d, then this observer will observe that the light is traveling the distance 2d. Okay, so if it is moving, this whole system is moving in this direction, so then what will happen? So this is the system, this is the beam of light, and so at this instance it is here, suppose, and at this instance it is striking the reflector, then again it is reflected back, and so on. Okay, so here is this is the same system, it is moving in this direction, in this way. So now you see, so here is the light, beam of light here is striking, and it is reflection, it is reflected, and this is the reflected beam of light, and it reaches the detector. So here you see, if you observe the motion with respect to this observer, the light is traveling this distance. Okay, that means for this observer, so suppose here this instrument is here, suppose, and final position is here. So let me draw it more clearly. Okay, so here is the instrument, it is moving in this direction. So this is the light of beam that you can see in green color. So it's traveling like this, and here it strikes, here is the reflector, then it will be reflected back this way, and here is the detector also, as well as the source. So an observer moving with this instrument, and he also has a clock with him to measure the time. Okay, so according to this observer O this, and this is suppose O, this observer on the earth is O, and this is O this. So this distance, if this is d, then he will observe that light is traveling twice d. So, and when it reaches to this position, suppose the time recorded is 1 minute, and time will be recorded in this clock also 1 minute. But here you see, so according to this observer, the path is this one. This is the distance traveled by the light, beam of light, and whereas according to this observer, the distance traveled by this light is only this part, this one, and then reflected back to this. Okay, so that is twice d. Now you see, from here to this position, suppose it is x. If it is x, then it must be also x from here to there. Okay, and this length is suppose L. This is suppose L, and here it is d. Now you see, if you apply Pythagoras theorem and if you calculate this L, if you calculate this L using Pythagoras theorem here, then you will get that let me tell you one more thing. According to this observer on the earth surface, the light this beam light of beam travels this distance x, and x, that is twice x. Okay, it travels twice x. So if you calculate twice x, if you in terms of d and L, then you will get twice x is equal to 2 root over L square plus d square using Pythagoras theorem. Okay, and here we know that distance is equal to speed into time. Speed into time. Now you see, in this case, the distance traveled by this light, beam of light, for this observer O this in the space is twice d. So twice d is the distance, and the speed of light is c, and time we have considered suppose t. In this case is recorded 1 minute, suppose for simplicity let us consider 1 minute, and this t is equal to 1 minute. And for this observer standing on earth surface, so the distance is twice x, which is equal to root over 2 L square plus d square, that is speed of light according to special theory of relativity remains constant, c into here also time t. So time recorded on earth is also 1 minute, in this case also 1 minute. But here you see, as c is constant, c is constant, and here you see this length is obviously greater than twice d. Okay, so then this time cannot be same. So that what does it mean? Because you see, as c is constant here, and these differences these distances are different. Okay, so this distance is 2 root over L square plus d square. It is obviously greater than twice d, so that's why. So 1 minute, which is recorded in space, and 1 minute recorded in art, though this time in both cases seems to be 1 minute. So to satisfy this equation, that this condition that speed of light is constant, this 1 minute in the space must be longer than the time recorded in art, that is 1 minute. That means the clock which is in the space, that is, it is running slower comparatively to the clock which is on the earth surface. So that is what we used to say time dilation. Okay, so now the mathematical expression of time dilation is this one. Here del t is the time dilation, or the which is change in time in the two frame of references that we have considered. One, this instrument that emits light and reflect light, that is in space, that is another frame of reference. There was an observer, and one observer on the earth surface that we have assumed in the example that I have explained already. So the time difference in these two frame of reference is given by this del t, and time recorded on the frame of reference initial this on earth, that is del t naught, and the relative velocity of these two frame of reference, this one and this, with respect to the earth, it is moving with velocity v, and the speed of light this speed of light that is uh, emitted by this instrument and reflected by this instrument, that is c. So time dilation is given by this expression. So I will show you how to derive this equation in another video. Okay, so I will make 2 or 3 more videos to cover uh, the topics, including the derivation of this equation. I'll cover more topics that let me show you in the next 2 or 3 videos. We are going to cover these topics: Galilean transformation, Lorentz transformation, length contraction, and simultaneity, law of variation of mass, and Einstein work energy relation. And those things will be covered in 2 or 3 videos maybe. So thank you for watching.